Good morning. In our course selected topics in decision modeling, today we are in our 27th lecture, that is constrained nonlinear programming KKT conditions, that is Karush-Kuntaka conditions. We have seen that how to solve nonlinear programming problem with equality constraints in our last class. There we had used Lagrange's multipliers and differentiated the function to find out conditions for optimality. Whereas for inequality constraints, Lagrange's multiplier cannot be utilized. We need to go for a little more involved calculations with the help of KKT conditions. Some of the basic features: the objective function can be linear or nonlinear, constraints can also be linear or nonlinear, and constraints can be of any type, that is inequality or equality. If you recall, I have told in our last class that the Lagrange's multiplier is a special case of KKT conditions. So, at some other time I will also show you that how it is really happening. So, you see, any linear programming problem can be put in maximization general form. If it is not happening, then we must ensure how to do it. Is it all right? So, the first of all, let me just tell this right in the beginning that all the conditions and all the discussions that we are going to have, we shall assume the programming problem, the nonlinear programming problem is available in the general form, that is maximize f, which is a function of x. Really speaking, x is having several variables x1, x2 to xn, and subject to conditions hix less than equal to bi, where I is 1 to m. Is all right. So, that is the general form that we are going to use for all the KKT conditions. Now, Karush-Kuntaka conditions, or in short KKT conditions, were obtained by Kuntaka, but then Karush independently obtained them actually earlier, right, in his thesis work. So, that is the reason why these conditions are known as Karush-Kuntaka conditions. But just remember this, that these conditions, they are not the only conditions required for optimality. In fact, they are only the necessary conditions, right. So, KKT conditions are the necessary conditions for the NLP problem. The sufficiency condition is still the for the maximization problem, the fx should be concave and each constraint should be convex. Is it all right? So, you just recall our discussions that for maximization what you require, the objective function should be concave and the constraint should be convex. Now, sometimes we have linear constraints, the linear constraints are both convex and concave at the same time. So, if I have linear objective function, then automatically we can assume the objective function to be concave, or if we have constraints, some of the constraints are linear, then those linear constraints can be also assumed to be convex, because linear constraints or objective functions are both concave and convex at the same time. But if it is nonlinear, then the concavity has to be seen either by the nature of the plot or by obtaining the second differential, that is in when multiple variables are involved, then obtaining the Hessian matrix. So, we shall see that in due course of time. Right. So, let us look at the KKT conditions. So, first of all, when we are solving in a general approach to constrained nonlinear problems, let us assume that we have certain functions, that is f x, g I x, g 1 x, g 2 x to g m x, they are all differentiable functions and having certain regularity conditions as well. Then the x star, which is a combination of n unknown variables or decision variables, can be an optimal solution for the NLP problem only if there exists m number of multipliers u1 to um such that a number of KKT conditions are satisfied. So, what are the things that we said? Just imagine, just remember that our original problem was maximizing f x subject to number of conditions, that was g I x less than equal to b I. So, they all should be differentiable, that is first requirement, and there exist certain multipliers, that is u1 to um. Along with them we have those KKT conditions which must be satisfied for x star to become optimal, right. So, these are the certain preconditions. Now, let us look at the KKT conditions. So, the first condition, as you can see, is del f del x j minus the sum over all the ui's. I mean each the sum is taken over each of the constraints ui del g I del x I j less than equal to 0. That is the first condition valid at the optimal point and for each of the x variables. So, this is more like the differential condition, but the condition you see we have the objective function and we also have a series of constraints. So, if I multiply those constraints by our multiplier, that is the ui's. So, each, say first constraint multiply by u1, second multiply by u2, third by u3, etcetera, etcetera, and then we differentiate by taking appropriately, that is very important, the negative sign. This negative sign of combination usually is used for maximization problem. Sometimes plus is used for minimization, but we can generalize with negative also. We will have some discussion later. The second condition is just the first part, whatever the first condition left hand side you see the same portion. So, if you see the first part, see this is the LHS of the first condition. So, this is the LHS of the first condition. So, that multiplied by xj star, is it all right. So, the LHS, whatever the differential part you get for the first condition, if you multiply by xj star, that should be 0, that is the second condition. That means, either this first constraint is equality or xj equal to 0, xj star equal to 0. So, what that second condition says is that either the first condition is an equality or the corresponding x variable, that is xj star, should be equal to 0. Is all right. That is the second condition says. The third condition is again very straightforward, because we see that g I x is less than equal to b I, that is our specific constraint. So, it is the same constraint written in another form. So, really the third constraint is nothing new, because the original constraint we have is g I, say x 1 less than equal to b I. So, the same constraint we have written in this form. So, this is the constraint itself, and at x 1 equal to x 1 star, at x 1 equal to x 1 star, this should be star. So, see, this was our original constraint, and so the same original constraint has been rewritten in this form. So, that is our third constraint. So, you can understand that although they look rather big, but really speaking the constraints are very simple. In fact, the first one is nothing but the differentiation should be less than equal to 0. The second condition is either the LHS of the first condition that becomes 0, that means del f del x j should be equal to this term, or the corresponding x variable should be 0. And the third one is nothing but the constraints, the corresponding constraints themselves, right. So, we have seen those first three conditions. Let us see the last few conditions. So, see, like we said in the case of the constraints, the differentiation. So, our original constraints has been rewritten as g I x star minus b less than equal to 0. So, b I. So, that is has been written. So, again, so multiply by the corresponding multiplier, multiply by the corresponding multiplier should be equal to 0. So, that is the fourth condition. So, once again, and fifth and sixth condition should be all the multipliers should be greater than equal to 0, and all the decision variable at the optimal point should be also greater than equal to 0. So, these are our 6 KKT conditions. So, just look at them once again. The if you really see, then the So, these are the KKT conditions. The first condition is the differential partial differentiation with respect to each variable. So, we had n unknown variable, each variable should be taken one at a time. The first part is the objective function part, the second part is the individual constraints multiplied by the multiplier, and then taking the negative of the the partial differentiation. The second constraint is the LHS of the first part should be either 0 or the corresponding decision variable should be 0. The third constraint is the original the constraint itself written in another form. The fourth constraint is either the it becomes equality, the constraint become equality, or the corresponding Lagrange the multiplier become equality. And the fifth and sixth conditions are basically non-negativity constraints, both for the decision variables and for the multipliers. Is it all right? So, this is how we begin with the KKT conditions. These are the 6 KKT conditions. So, for improving our understanding, let us look at a particular problem, a very simple one, simplified version of the KKT conditions once again. So, let us say we have a 2 variable problem, maximize f x 1 x 2. So, a function which is having f x 1 x 2 and subject to 2 constraints only, that is g 1 x 1 x 2. In short, we can also write this thing as this, that maximize f x subject to g 1 x less than equal to b 1 and g 2 x less than equal to b 2. So, that is all is our problem, very simple problem we take. Now, the condition that is required is all the three functions, that is f x, g 1 x and g 2 x, should be differentiable, that is a requirement. Now, x star equal to x 1 star x 2 star can be an optimal solution for the NLP problem if and only if there exist u 1 u 2 two multipliers such that they are actually equivalent to Lagrange's multipliers. So, such that all the KKT conditions are satisfied. Is it all right? So, this is the requirement. So, let us see once again what exactly is these conditions are essentially. So, first condition, you see, suppose I write a function, let us say total the function, the combination function. So, let us call it combined function. The combined function is f x minus u 1 g 1 x minus u 2 g 2 x. So, what is this combined function? This combined function is obtained by combining the function f x along with the two constraints g 1 x less than equal to b 1 and g 2 x less than equal to b 2. So, if I combine them, then what you get is f x minus u 1 g 1 x minus u 2 g 2 x. So, now you see the first constraint is nothing but the differentiation of these function with respect to x 1 and with respect to x 2. So, please differentiate these with respect to x 1, what do you get? Del f del x 1 minus u 1 del g 1 del x 1 minus u 2 del g 2 del x 1. So, precisely that is what is written. Here g 1 is nothing but g 1 x, g 2 is nothing but g 2 x. So, that should be less than equal to 0, that is the first condition. So, similarly, the second condition is again the differentiation of the combined function, that is del f del x 2 minus u 1 del g 1 del x 2 minus u 2 del g 2 del x 2 less than equal to 0. So, that is the second condition of the first condition, second part. The second condition again will be the either these partial differentiation of the combined function should be equal to 0 or the corresponding optimal variable that at the optimal point. So, either the equation becomes equality or the variable corresponding variable is 0, right. So, either this equal to 0, right, this term is 0 or the corresponding decision variable equal to 0. Same thing holds for x 2 also. So, I hope the first two conditions, which are the most important KKT conditions, you have understood clearly. Is it all right? So, if you have understood these two conditions clearly, let us see the remaining conditions. The remaining conditions are again for the same problem, how the third condition is nothing but the constant itself, that is g 1 x 1 x 2, or we can write g 1 x less than equal to 0 and g 2 x 1 x 2 minus b 2 less than equal to 0 at the optimal point. So, the star we can write star sometimes, but to make for simplification we may not write star in between calculations, but we should know that we are calculating the variable at the optimal point, because all these KKT conditions are true not always, but at the point of optimality. Is it all right? All right. So, that is the third condition, and the fourth condition is either these constraints become equality or the corresponding multiplier becomes 0. Is it all right? So, that is what is essentially they say. These are the fourth conditions. The fifth conditions are the at the optimal point the variables should be greater than equal to 0. The sixth condition has not come properly. So, that should means u 1 should be greater than equal to 0 and u 2 should be greater than equal to 0, right. So, these are the 6 conditions. So, this is how you can see that how the at the optimal point the necessary conditions are that the KKT conditions must hold, right. So, you understood. So, once again that we are having nonlinear programming problem with inequality constraints, which also includes the equality constraints also. In fact, equality constraints are a special case. In case of equality constraints, really see what happens. These automatically become 0. So, if these become 0, so it is not really necessary that u 1 and u 2 to become 0 also, and the first constraints then become trivial. Is it all right? So, we will discuss it some other time. Now, let us look at a particular problem and see how optimal solution can be obtained for a particular problem by making use of the KKT conditions, right. So, let us take this problem. Manufacturer uses a raw material to produce product A and product B, right. Now, for producing these product A and product B, first of all there is a cost. The cost is 30 rupees per kg for A and 50 rupees per kg for B. Now, the cost of raw material is rupees 100 per kg and maximum available raw material is 40 kg, right. The selling price of each kg of A and B follow the given price formula. What is the price formula? The selling price of A is 200 minus 2 into quantity of A and selling price of B is 250 minus 3 into quantity of B. So, determine the optimal quantity of product A and product B to be produced for maximization of profit, right. So, this looks like a simple optimization problem, but there is a catch. The selling price is not linear. I mean it is linear now, but when you convert it to objective function, then it will become non-linear, right. So, let us see how to formulate the problem first. So, these are the decision variables. Suppose x 1 is the amount of product A to be produced in kg, x 2 is the amount of product B to be produced in kg and x 3 is the amount of raw material used, is all right. So, what is the profit equation? Profit will be quantity into selling price minus cost, is all right. So, what is the quantity? Quantity is x 1 and x 2. What is the selling price? 200 minus 2 into quantity, that is 200 minus 2 x 1 and here 250 minus 3 x 2, right. So, that will be the quantity into selling price. And what is the cost? Cost is 30, 50 and 100. So, 30 x 1, 50 x 2, 100 x 3. Is it all right? So, that is the thing that therefore, you can simplify. So, you see this is 200 x 1 minus 30 x 1. So, 170 x 1, 250 x 2 minus 50 x 2. So, 200 x 2 and minus 2 x square minus 3 x 2 square minus 100 x 3. So, this is our objective function, right. So, first part is done. So, we have obtained the profit, but there are some constraints also, right. So, what is the constraint? The constraint is very clear that the two product x 1 and x 2 should not be, the sum of these should not be more than the raw material available, because that is a constraint. You cannot produce without the raw material. So, let us see what is that constraints. Yeah, so let us see that. See, the constraint therefore will be x 1 plus x 2 less than equal to x 3. Why? Because this is the first product, this is the second product. So, if you add them, that should be less than the raw material, that is the quantity x 3. So, this can be reformulated as x 1 plus x 2 minus x 3 less than equal to 0. So, see, this side is the variables and this side, because x 3 is not B I. So, B I has to be a constant, right, cannot be a variable. So, since here we have a variable called x 3, so obviously it should be put as x 1 plus x 2 minus x 3 less than equal to 0. So, this 0 is like B I. So, this is our B I, these are the variables, right. So, that is what we have, that the first constraint. Now, the second constraint is also there, that is x 3 should be less than 40, because that is the total amount. If you look at the problem, that is the total amount that is available, and obviously since it is a real problem, x 1, x 2, x 3 all should be greater than equal to 0. So, that is our starting point. We have an objective function, that is f x 1, x 2, x 3, and maximize 170 x 1 minus 2 x 1 square plus 200 x 2 minus 3 x 2 square minus 100 x 3, and these are our constraints, right. So, the first question is, how do we go ahead solving the problem? But before even that, we should see that if we take the KKT conditions now, the KKT conditions will really provide the necessary conditions. The sufficient condition should be, we have to ensure that the function is concave. Now, incidentally, this function is concave, but then can we take the Hessian matrix and find out whether the matrix is really concave. I mean, this objective function is really concave. No problem about constraints, because constraints are all linear. So, all of them are linear constraints. So, with the linear constraints, automatically they are convex. So, no issue there. So, let us see how we can see that these are concave. So, objective function is the sum of concave functions. So, if they are, automatically the second order differentiation would be negative, that is, it proves concavity. Constraints are linear, so therefore, they can be taken as convex. Therefore, if some solution could be found to satisfy all the KKT conditions, then the resulting solution will be optimal, as it satisfies both necessary and sufficient conditions. So, let us look at the Hessian matrix. So, you see, this is our function, right, that is the total function, this is a simplified function 170 x 1 minus 2 x square plus 200 x 2 minus 3 x 2 square minus 100 x 3. So, the gradient will be del f del x 1, del f del x 2, del f del x 3. So, what should be with respect to x 1, if you differentiate, you get 170 minus 4 x 1. With respect to x 2, 200 minus 6 x 2, and with respect to x 3, minus 100. So, this is our gradient. So, we got the gradient. Next will be the Hessian matrix. Now, you see, since they are pure terms of x 1 and x 2, so all these terms, they will be 0. So, all of them are 0. So, with respect to this, del square f del x 1 square, that becomes minus 4, del square f del x 2 square, that becomes minus 6, and since there is no term, this will become 0. So, this is our Hessian matrix, right. So, we obtained the Hessian matrix. Now, we take the eigenvalue by making use of characteristic equation, and this is the eigenvalue equation, and very simple this one, it comes to this kind of equations, that is 4 plus lambda plus star 6 plus lambda star lambda equal to 0. So, 3 different values of lambda could be -4, -6 and 0. So, all the eigenvalues are less than equal to 0. So, what is our conclusion? The conclusion is the Hessian matrix is negative semi definite, because one of the term is 0. So, automatically since the eigenvalues are negative, only one is 0. So, we can say the function is concave and we can have maximum value out of this. Is all right. So, I stop here. In our next lecture we continue the discussion on KKT conditions. Specifically the problem that we are doing, we shall complete the one.